Hello everyone, Dr. Mohammed Ali here, ready to continue our exploration into the fascinating world of physics. Today, we're diving into Chapter 4, Part 2, Thermal Physics. Last time, in Part 1 of Chapter 4, we explored fundamental concepts like heat, temperature, different temperature scales, and the fascinating world of thermal expansion, including linear, area, and volume expansion, and even its implications in dentistry and the unique behavior of water. Today, as we move into Part 2, we'll continue our journey into thermal physics. We'll dive into the connection between heat and mechanical work, understand heat capacity and specific heat, learn about calorimetry, and explore latent heats. Then, we'll shift our focus to the different ways heat is transferred, through conduction, convection, and radiation, and finally, we'll conclude with an introduction to the first law of thermodynamics and its applications, even to human metabolism. It's going to be a comprehensive and exciting session. Let's get started. Here is a fascinating concept that bridges the world of physical effort with the invisible flow of thermal energy, heat and mechanical work. You know, if you rub your hands together vigorously, what happens? They get warm, right? That's mechanical work, the friction of your hands moving, being converted directly into heat. It's a fundamental principle, showing us that energy isn't lost, it just transforms. Now, when we talk about heat, we need to have units to measure it, just like we measure length in meters or time in seconds. Our slide introduces a couple of key units for heat. First, we have the kilocalorie, which you might see abbreviated as kilocalories, or sometimes just calorie with a capital C, or even simply C. This isn't just a number, it has a very precise definition. 1 kilocalorie is defined as the amount of heat needed to raise the temperature of exactly 1 kilogram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. It's a very specific, historical definition, rooted in early experiments. And here's an important equivalence: 1 kilocalories is exactly equal to 1 calorie, with a capital C, and also equal to 1 C, capital C. Why the capital C? This is where it gets interesting. In everyday nutrition, when you look at a food label and see calories, they're actually referring to kilocalories. So, a 250-calorie candy bar isn't 250 small c calories, it's 250 kilocalories, which is a whopping 250,000 small c calories. Nutritionists use the capital C as a shorthand because who wants to write all those zeros on a food label? But in physics, we need to be very precise. If you see a capital C in a physics problem, always remember it means kilo, and if you need to convert to the smaller c calorie, you multiply by 1,000. Next up, we have the mechanical equivalent of heat. This concept was brilliantly established by James Prescott Joule, who showed that mechanical energy can be converted into heat and vice versa. His experiments gave us the precise conversion factor between the calorie, the small c calorie, the basic unit, and the joule, J, which is the SI unit for energy and work. We find that 1 calorie is equivalent to 4.186 joules. And logically, if 1 kilocalorie is 1,000 calories, then 1 calorie, capital C, is equivalent to 4,186 joules. This conversion is super important because it allows us to relate the energy content of food, for example, to the mechanical work our bodies can do. Finally, we encounter another unit of heat, popular in specific industries, especially in regions that follow the British imperial system, the BTU, or British thermal unit. Just like the kilocalorie, it has a precise definition: it's the energy required to heat 1 pound, lb, of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit. Notice the different units here, pounds for mass and Fahrenheit for temperature, reflecting its origin. And how does it relate to the other units we've discussed? 1 BTU is equivalent to 0.252 kilocalories, which, if you do the math, comes out to approximately 1055 joules. So, if you're ever dealing with natural gas, for instance, you'll often hear quantities measured in BTUs. It's a versatile unit for energy, but important to know its relation to the joule and calorie. So, this slide gives us a foundational understanding of how we quantify heat and its relationship to mechanical work, laying the groundwork for much more exciting thermal physics to come. We've learned about the different currencies of heat, the kilocalorie, the calorie, and the British thermal unit, and their crucial exchange rates with the joule, the universal currency of energy. Keep these conversions in mind, as they are your tools for navigating the fascinating world of thermal physics. Let's explore an interesting real-world application of thermal physics and energy conversion with example 4-4, the StairMaster problem. Here, we have a 74.0 kilogram person who decides to enjoy a thick, rich, 305-calorie milkshake. The question is, how many stairs must this person climb to work off that shake? We're told the height of a single stair is 20.0 centimeters. Now, this is a classic scenario where we convert the chemical energy stored in food into mechanical work. Think of it like adding fuel to our human engine. Our first step, as shown on the slide, is to convert the energy of the milkshake into a standard physics unit, joules. You'll notice the problem states 305 C milkshake with a capital C. Remember our discussions about units? In nutrition, a capital C in calorie actually means a kilocalorie. So, 305 C is 305 kilocalories. To convert this to joules, we use the conversion factor that 1 kilocalorie is equivalent to 4,186 joules. So, Q equals 305 kilocalories times 4,186 J divided by kilocalorie. This gives us approximately 1.28 by 10 to the power of 6 joules. That's a significant amount of energy. Next, this energy from the milkshake, once metabolized, is used to do work against gravity when climbing stairs. The work done against gravity is stored as gravitational potential energy. Remember our apartment building analogy? To climb to a higher floor, you need to exert energy, increasing your potential. The formula for this work, or potential energy, is Q equals mgh, where m is the person's mass, g is the acceleration due to gravity, 9.81 meters per second superscript 2, and h is the total height climbed. We know the energy, Q, from the milkshake, the person's mass, m, and g. We need to find the total height, h, this person must climb. Rearranging the formula, h equals Q divided by mg. Plugging in our values, h equals 1.28 by 10 to the power of 6 J, divided by 74.0 kilograms times 9.81 meters per second superscript 2. Calculating this, we find h equals 1760 meters. Now, that's the total height this person needs to climb. But the question asks for the number of stairs. This is like figuring out how many individual steps you need to take to reach the top of our metaphorical apartment building. We know each stair has a height of 20.0 centimeters. Of course, we need to convert that to meters to be consistent with our total height. 20.0 centimeters is 0.20 meters. So, to find the number of stairs, we simply divide the total height, h, by the height of a single stair. Number of stairs equals 1760 meters divided by 0.20 meters divided by stair. This gives us a whopping 8,800 stairs. Now, 8,800 stairs, that sounds like quite an intense workout, doesn't it? This brings us to a crucial point about the logic behind this calculation. In reality, our bodies are not 100% efficient at converting food energy directly into mechanical work. An actual human body, much like any engine, has a metabolic efficiency. For climbing stairs, this efficiency is typically around 20 to 25%. This means that only about 20 to 25% of the energy from that milkshake is actually used for the mechanical work of lifting your body. The rest is converted into heat to maintain body temperature, used for other metabolic processes, and lost to the environment. So, if we were to consider this real-world efficiency, the actual number of stairs you'd need to climb just for the mechanical work would be less, but you'd still have to consume the total energy. This problem, by assuming all energy is converted, gives us the theoretical maximum work output. It's a great example to illustrate the sheer amount of energy contained in our food, and why it's so challenging to burn off those extra calories. Here is a fascinating concept that helps us understand how different materials respond to heat capacity, denoted by the capital letter C. Think about it this way, not all materials behave the same when you try to heat them up, right? Some get hot very quickly, while others take a long time to warm up. Heat capacity is precisely about quantifying this difference. The slide defines heat capacity as the amount of heat, Q, necessary for a given temperature change, delta T. In simpler terms, it's how much energy, in the form of heat, you need to add to an object to make its temperature go up by a certain amount. From this definition, we can derive our fundamental equations for heat capacity. The first one directly reflects the definition, C equals Q divided by delta T. So, C equals Q divided by delta T. This tells us how much heat per unit temperature change a substance can hold. And, of course, if we rearrange that equation, we get the more co-millimeters only used form, Q equals C delta T. This formula is incredibly useful because it allows us to calculate the amount of heat, Q, transferred when an object with a known heat capacity, C, undergoes a specific temperature change, delta T. What about the units? Physics is precise. Since Q, or heat, is a form of energy, its SI unit is joules, J. And delta T, the change in temperature, can be measured in Kelvin, K, or degrees Celsius, C degrees. Remember, a change of 1 degree Celsius is exactly the same as a change of 1 Kelvin. So, the unit for heat capacity C is joules per Kelvin, J divided by K, or joules per degree Celsius, J divided by C degrees. Simple, right? Now, let's talk about the sign of Q. This is very important for consistency in our calculations. If Q is positive, it means that the change in temperature, delta T, is also positive. What does a positive delta T mean? It means the temperature of the system increased. And how does that happen? Because heat is added to the system. It's gaining energy. Conversely, if Q is negative, it implies that delta T is also negative. A negative delta T signifies a decrease in temperature. This occurs when heat is removed from the system. It's losing energy to its surroundings. Think back to our Ahmed and Hussein analogy. If Ahmed loses money, negative Q, then Hussein gains money, positive Q for Hussein. Here, we're focusing on one system. If your system loses heat, Q is negative. If your system gains heat, Q is positive. It's all about perspective. Finally, let's consider what heat capacity depends on. This is crucial for understanding why different objects have different C values. First, C depends on mass. Imagine you have a tiny droplet of water and a whole 3 millimeters in pool of water. To raise the temperature of the tiny droplet by 1 degree, you need a very small amount of heat. But to raise the temperature of the entire 3 millimeters in pool by 1 degree, you'd need an enormous amount of heat. This is because there's much more stuff in the pool to heat up. More mass means more particles, and each particle needs energy to increase its vibrational motion, which translates to a temperature increase. So, generally, the more mass an object has, the larger its heat capacity. Second, C depends on the type of material. This is intuitive, isn't it? If you put a metal spoon and a wooden spoon in a hot pot of soup, which one gets hot faster? The metal spoon, of course. Metal has a different atomic structure and different ways of transferring energy compared to wood. This inherent property of the material itself dictates how much heat it takes to change its temperature. Even if you have the same mass of two different materials, say, a kilogram of iron and a kilogram of aluminum, they will have different heat capacities because they are fundamentally different substances. So, heat capacity C is a measure of an object's ability to store thermal energy. It's a macroscopic property that tells us about the object's overall thermal behavior, taking into account both how much material there is and what that material is made of. It's like asking, how much heat can this specific apartment building hold before its internal temperature changes too much? That depends on its size, mass, and what it's built from, type of material. Turning our attention to, we have exercise 4-3, a straightforward application of what we've just discussed about heat capacity. Here, we're given the heat capacity of 1 kilogram of water, which is a rather significant 4,186 joules per Kelvin. This value tells us how much energy is needed to change the temperature of this specific amount of water by 1 degree Kelvin. Remember our discussion about how different substances, and even different amounts of the same substance, hold on to or release heat differently. Water, with its high heat capacity, is quite special in this regard. The problem asks us to find the temperature change, delta T, under two scenarios: first, when heat is added to the system, and second, when heat is removed from it. Let's tackle part A, first. Calculate delta T for Q equals 505 J. We know the fundamental relationship, heat capacity, C, is the amount of heat, Q, transferred per unit change in temperature, delta T. So, C equals Q divided by delta T. If we want to find the temperature change, we simply rearrange that to delta T equals Q divided by C. In this case, Q, the heat added to the system, is 505 joules. The heat capacity, C, is given as 4186 joules per Kelvin. So, we divide 505 J by 4186 J divided by K. This calculation gives us a temperature change of 0.121 Kelvin. Notice something important here, Q is positive, meaning heat was added to the system. And our delta T is also positive, indicating that the temperature increased. This aligns perfectly with our sign convention, adding heat usually leads to a temperature rise, a gain in temperature, if you will. Now, for part B, what if 1010 J of heat is removed? This is where our sign convention becomes crucial. When heat is removed from the system, we must denote Q with a negative sign. So, Q becomes minus 1010 joules. The heat capacity of the water, of course, remains the same at 4186 J divided by K. Using the same formula, delta T equals Q divided by C, we now have delta T equals minus 1010 J divided by 4186 J divided by K. Performing this calculation, we get a delta T of minus 0.241 Kelvin. Observe the negative sign on our delta T. This tells us that the temperature decreased. Again, this makes perfect sense, removing heat from a system causes its temperature to drop. It's a loss of heat resulting in a negative temperature change, exactly as we would expect. So, whether we're adding heat or removing it, the heat capacity tells us how much the temperature will shift, and the sign of Q guides us on the direction of that shift. A very handy and consistent convention, wouldn't you agree? Let's explore the fascinating concept of specific heat capacity, which we denote with the small letter C. Slide title, Specific Heat Capacity, C. Think of specific heat capacity as a material's thermal inertia, or its ability to resist changes in temperature when heat is added or removed. The definition on our slide says it beautifully, it is the amount of heat required to increase the temperature of 1 kilogram of substance by 1 degree Celsius. So, for every kilogram of a material, how much energy, how many joules, do I need to put in to nudge its temperature up by just 1 degree Celsius? Or 1 Kelvin, since a change of 1 degree Celsius is the same as a change of 1 Kelvin. Now, from this definition, we get a very important formula, C equals Q divided by m delta T, where C is the specific heat capacity, Q is the amount of heat transferred, m is the mass of the substance, and delta T is the change in temperature. If we rearrange this, we get the more co-millimeters only used formula, Q equals mc delta T. This tells us that the heat, Q, needed is directly proportional to the mass, the specific heat, and the temperature change. And what are its units? Unit, joules per kilogram Kelvin or joules per kilogram. C degrees, yes, joules per kilogram per Kelvin, or joules per kilogram per degree Celsius. Simple, right? Table 4, 2 specific heats at atmospheric pressure. Now, let's look at the table on our slide. This table shows you specific heat values for many co-millimeter sun materials. Bullet point, C depends on the type of material. See the table. This is crucial. Specific heat, C, is an intrinsic property of the material itself. It doesn't depend on how much of the material you have, just what it is. This is different from the overall heat capacity, capital C, we discussed before, which does depend on the mass. Specific heat, with the small c, is specific to the substance. Notice something extraordinary in this table, water. Table, water, 4186, water has an incredibly high specific heat capacity, 4186 joules per kilogram Kelvin. Compare that to lead, down at the bottom, table, lead, 128, only 128 joules per kilogram Kelvin. This is a massive difference. Bullet point, for a given delta T, Q increases C of material. This means if you want to raise the temperature of 1 kilogram of water by, say, 10 degrees, you'll need significantly more heat, Q, than to raise the temperature of 1 kilogram of lead by 10 degrees. Water is like that person who's always calm and collected, you have to throw a lot at them before they even flinch, change temperature. Lead, on the other hand, is much more excitable. Bullet point, C alpha 1 divided by delta T for constant Q and M. Let's think about this inverse relationship. If I give the same amount of heat, Q, to the same mass, M, of two different materials, the one with the smaller specific heat, C, will experience a larger change in temperature, delta T. Remember our apartment building analogy? Imagine specific heat capacity as how much stuff, heat energy, a certain volume of space, a kilogram of material, can absorb before its temperature, its internal state of agitation, visibly changes a lot. Water, with its huge specific heat, is like a massive, well-insulated apartment building. You can pour in tons of heat, and the internal temperature barely nudges. But something with a small specific heat, like lead, is like a tiny, poorly insulated shed. A little bit of heat, and whoosh, the temperature shoots up. Take a look at the image on the right. You see blocks of aluminum and lead. Now, let's peek at our table. Aluminum has a specific heat of 900 joules per kilogram Kelvin, while lead is a mere 128 joules per kilogram Kelvin. If I put both of these on a hot plate and give them the same amount of heat, which one do you think would get hotter faster? The lead, right? Its specific heat is much lower, meaning it takes less energy to raise its temperature by 1 degree. Aluminum, on the other hand, needs much more heat to experience the same temperature rise. It's much better at storing that heat without its temperature skyrocketing. Bullet point, note that the specific heat of water is by far the largest of any co-millimeter sun material. Unusual properties. Having such a large specific heat means that water can give off or take in large quantities of heat with little change in temperature. This unusual property of water is incredibly important for life on Earth. Think about it, our bodies are mostly water. This high specific heat helps us maintain a stable internal body temperature even when the outside world is heating up or cooling down. Without it, a slight change in external temperature would cause drastic changes in our internal temperature, and that wouldn't be good news. It's also why coastal climates are often milder than inland climates. The enormous specific heat of the ocean allows it to absorb vast amounts of solar energy in the SU millimeters and release it slowly in the winter, moderating temperature swings for nearby land. And here's a little bit of humor, something to remember when you're enjoying your next meal. Have you ever bitten into a hot pie, and the crust is warm, but the fruit filling inside incinerates your tongue? Light humor, that's because the fruit filling, being mostly water, has a much higher specific heat than the drier crust. It can store a much larger quantity of heat at a given temperature, and it releases that heat into your poor tongue. So, specific heat capacity isn't just a number, it's a fundamental property that explains so much about how materials, and even our world, interact with heat. It truly defines how much of a thermal shock absorber a substance can be. Another key point is a very practical application of everything we've been discussing about heat and specific heat, and that's what we call calorimetry. Now, imagine this scenario, a classic setup. Suppose we have a block, let's give it a mass mb, a specific heat cb, and an initial temperature tb. This block is then carefully dropped into a calorimeter. What's a calorimeter, you ask? Well, it's basically a very clever, lightweight, and insulated flask. Think of it like a super-efficient thermos, designed to prevent any heat from escaping or entering from the outside. Inside this flask, we have water, with its own mass mw, specific heat cw, and initial temperature tw. Our goal here is to find the final temperature, T, once everything settles down. There are two fundamental ideas, two pillars, if you will, that underpin solving any problem like this. First, once our block and water are in thermal contact within that insulated calorimeter, they will eventually reach what we call thermal equilibrium. This means they'll both end up at the same final temperature, T. This is crucial, they keep exchanging heat until they can't anymore because their temperatures are identical. Second, and this is where our Ahmed and Hussein story comes in handy, the total energy of the system must be conserved. Remember our analogy? If Ahmed lost 100 pounds from his pocket, and Hussein was the only other person in the room, then Hussein must have gained those 100 pounds. The total change in money within that isolated room is zero. It's the same principle here with heat. If the block loses heat, the water gains exactly that same amount of heat. If the water loses heat, because it was initially hotter than the block gains that heat. The sum of all heat changes, QB, heat change of the block, plus QW, heat change of the water, must equal zero. That's our fundamental conservation law for an isolated system. Now, if we take these heat terms, QB and QW, and express them using our specific heat formula, remember, Q equals mcΔT, and we let T be that final, equilibrium temperature, here's what happens. For the block, its heat change QB will be its mass mb, times its specific heat Cb, times its change in temperature. The change in temperature is always the final temperature minus the initial temperature, so that's T, Tb. Similarly, for the water, its heat change Qw will be its mass Mw, times its specific heat Cw, times its temperature change, which is T, Tw. So, substituting these into our conservation of energy equation, Qb plus Qw equals 0, we get MbCb, T, Tb, plus MwCw, T, Tw, equals 0. This equation, my friends, is your go-to for solving calorimetry problems. It elegantly captures all the heat exchange. And what if we want to find that final temperature, T? Well, with a bit of algebraic rearrangement, we can isolate T. Think of it as putting all the T terms on one side and everything else on the other. After we factor out T and divide, we arrive at this neat expression, T equals MbCbTb plus MwCwTw, divided by MbCb plus MwCw. This T is your final equilibrium temperature. It's like finding the average temperature, but a weighted average, where the weighting factors are not just the masses, but the product of mass and specific heat, Mc, which, you remember, is the heat capacity itself. So, materials with higher heat capacity, like water, have a stronger influence on the final temperature. So, when you see a problem asking about mixing substances and reaching a co-millimeter sun temperature, this calorimetry framework is your powerful tool. It's all about ensuring that in an isolated system, heat is simply redistributed, not lost or gained overall. No tricks, just good old conservation of energy. Another key point is this active example 4-2. This is where we take the concepts we've been discussing, particularly calorimetry and specific heat, and apply them to a real-world problem. It's like putting our physics toolbox to good use. The problem asks us to find the final temperature. Let's read it carefully. Suppose 550 grams of water at 32 degrees Celsius are poured into a 210-gram aluminum can with an initial temperature of 15 degrees Celsius. Find the final temperature of the system, assuming no heat is exchanged with the surroundings. This is a classic calorimetry problem. Remember our discussion about isolated systems? This is exactly that scenario, no heat escaping to the environment, only transfers happening within the system. Think back to our Ahmed and Hussein analogy. If Ahmed loses 100 pounds, Hussein must gain 100 pounds if they're the only two people in a sealed room. The total change in money within that room is 0. The same principle applies here, but with heat energy. Let's break down the solution steps presented on the slide. 1. Write an expression for the heat flow out of the water, Qw equals MwCw, T, Tw. First, we need to consider the water. The water starts at 32 degrees Celsius, and the aluminum can starts at 15 degrees Celsius. Since 32 degrees Celsius is warmer, the water is going to lose heat. So, its heat flow, Qw, will be negative. The formula for heat transfer, as we know, is Q equals mcΔT. Here, Mw is the mass of the water, 550 g, which will convert to 0.550 kilograms for consistency with our specific heat units. Cw is the specific heat of water, T is the final equilibrium temperature, what we're trying to find, and Tw is the initial temperature of the water, 32 degrees Celsius. From our textbook, Table 4-2, the specific heat of water, Cw, is 4186 J divided by kgK. So, Qw equals 0.550 kilograms, 4186 J divided by kgK, T, 32 degrees Celsius. 2. Write an expression for the heat flow into the aluminum, Qa equals mCA, T, Ta. Next, the aluminum can. It starts at a cooler 15 degrees Celsius. So, it's going to gain heat from the warmer water. Its heat flow, Qa, will be positive. Again, using Q equals mcΔT. Here, Ma is the mass of the aluminum, 210 g, or 0.210 kilograms, Ca is the specific heat of aluminum, T is the final temperature, and Ta is the initial temperature of the aluminum, 15 degrees Celsius. Looking at Table 4-2, the specific heat of aluminum, Ca, is 900 J divided by kgK. So, Qa equals 0.210 kilograms, 900 J divided by kgK, T, 15 degrees Celsius. 3. Apply energy conservation. QW plus QA equals 0. This is the core of our isolated system concept. All the heat lost by the water must be gained by the aluminum can. So, when we add the heat flows together, their sum must be 0. Whatever negative value QW has, QA must have an equal positive value, ensuring that the total energy change within our system is 0. No heat in, no heat out of the whole system. 4. Solve for the final temperature, T equals 31 degrees Celsius. Now, for the algebra. We set up our equation, MWCW, T, TW, plus MACA, T, TA, equals 0, plugging in our values, 0.550 kilograms, 4186 J divided by, kgK, T, 32, plus, 0.210 kilograms, 900 J divided by, kgK, T, 15, equals 0. Let's simplify. 2302.3, T, 32, plus 189, T, 15, equals 0. Distribute the terms, 2302.3 T, 2302.332, plus 189 T, 189.15, equals 0. 2302.3 T, 73,673.6 plus 189 T, 2,835 equals 0. Combine the T terms and the constant terms, 2302.3 plus 189, T equals 73,673.6 plus 2,835 2491.3 T equals 76,508.6 and finally, solve for T. T equals 76,508.6 divided by 2,491.3 is approximately 30.70 degrees Celsius. The slide rounds this to 31 degrees Celsius. It's satisfying to see the numbers align. The insight here is crucial, as one might expect from water's large specific heat. The final co-millimeter sun temperature, T, is much closer to the initial temperature of the water, TW, than that of the aluminum, Ta. This is a fantastic point. Water has a very high specific heat capacity compared to most other substances, including aluminum. What does that mean? It means water requires a lot of energy to change its temperature even a little bit, or conversely, it can give off a lot of energy while changing its temperature only a little. Aluminum, with a specific heat of 900 J divided by kgK, changes temperature much more readily than water, which is at 4186 J divided by kgK. So, even though we have less water, 550 G, than the combined amount of material, its large specific heat acts like a thermal anchor, keeping the final temperature much closer to its initial 32 degrees Celsius, rather than drifting heavily towards the aluminum's 15 degrees Celsius. If you put your hand in a tub of hot water, you feel the heat, but the temperature of the water itself won't drop dramatically unless you're a really big, cold object. Now, for your turn, suppose the can is made from iron rather than aluminum. In this case, do you expect the final temperature to be greater than or less than the value for aluminum? Find the final temperature for the case of an iron can. Let's think about this logically before doing any calculations. Iron specific heat, C iron, is 448 J divided by kgK, according to table 4.2. That's even less than aluminum's, 900 J divided by kgK. If the can has an even smaller specific heat, it means it takes even less energy to change its temperature. This implies the iron can will heat up more easily than the aluminum can would have, effectively taking less heat from the water to reach a certain temperature. If the can is less greedy for heat, the water will lose less of its initial heat, meaning the final equilibrium temperature should be closer to the water's initial temperature. So, I would expect the final temperature to be greater than 31 degrees Celsius. Let's quickly verify that with the numbers, using C iron equals 448 J divided by kgK, 0.550 kilograms, 4186 J divided by kgK, T, 32, plus 0.210 kilograms, 448 J divided by kgK, T, 15, equals 0. 2302.3, T, 32, plus 94.08, T, 15, equals 0. 2302.3 T, 73,673.6 plus 94.08 T, 1411.2 equals 02396.38 T equals 75084.8 T equals 75084.8 divided by 2396.38 is approximately 31.33 degrees Celsius. Indeed, 31.33 degrees Celsius is slightly higher than 30.70 degrees Celsius, which we rounded to 31 degrees Celsius. So, our prediction was correct. The final temperature would be greater. This example really highlights the practical application of calorimetry and specific heat in understanding how different materials interact thermally. Keep practicing these types of problems, and the concepts will become second nature. Here is a fascinating concept that brings together everything we've been learning about heat, temperature, and specific heat. This is example 4 to 5, aptly titled Cooling Off, Image, slide title, example 4 to 5 Cooling Off. Let's dive right into the problem description. We have a 0.50 kg block of metal, initially quite warm at 54.5 degrees Celsius. We then drop this metal block into a container of water. This container holds 1.1 kg of water, which starts at a cooler temperature of 20.0 degrees Celsius. The system eventually reaches thermal equilibrium, meaning everything settles at a single, final temperature of 21.4 degrees Celsius. Our mission: to find the specific heat of this mysterious metal block. We're told to ignore the container itself and assume no heat escapes to the surroundings, a perfect, isolated system. Image, initial conditions, diagram showing a block, TB, in a container of water, TW, with arrows indicating heat flow. Take a look at the diagrams here. On the left, we see the initial conditions. We have our block, with its own initial temperature, TB, and the water, with its initial temperature, TW. The block is hotter than the water, so what do you expect to happen? Heat will naturally flow from the hotter object to the colder object. Image, equilibrium, diagram showing the block and water at a co-millimeter sun final temperature, T, dot. Then, on the right, we see the equilibrium state. Both the metal block and the water have reached a co-millimeter sun final temperature, T, which is 21.4 degrees Celsius. This is a classic calorimetry problem. Now, remember our Ahmed divided by Hussein analogy? We talked about how, in an isolated system, if Ahmed loses 100 EGP, Hussein must gain 100 EGP. The total change in money within that closed room is zero. The same principle applies here, but with heat energy. The total heat exchanged within this isolated system must be zero. Whatever heat the metal block loses, the water gains. So, we can write our fundamental equation, Q block plus Q water equals 0. Let's think about the individual heat changes, Q. As we know, Q equals mc delta T, where delta T is the change in temperature, always calculated as the final temperature minus the initial temperature, T final, T initial. For the metal block, Q block equals m block C block, T block initial, here, the final temperature T, 21.4 degrees Celsius, is less than the block's initial temperature TB, 54.5 degrees Celsius. So, TB, will be a negative number. This means Q block will be negative, indicating that the block lost heat. This makes perfect sense, as it cooled down. For the water, Q water equals m water C water, T water initial, in this case, the final temperature T, 21.4 degrees Celsius, is greater than the water's initial temperature TW, 20.0 degrees Celsius. So, TW, will be a positive number. This means Q water will be positive, indicating that the water gained heat, which is also correct because it warmed up. Putting it all together, we have, m block C block, TB, plus m water C water, TW, equals 0. Our goal is to find C block, the specific heat of the metal. Let's rearrange this equation to solve for C block. First, move the water's heat term to the other side, m block C block, TB, equals, m water C water, TW, now, divide both sides by m block, TB, to isolate C block. C block equals, m water C water, TW, divided by, m block, TB, notice that negative sign in front. We can absorb it by flipping the terms in the denominator's temperature difference, changing TB to TBT. This makes the denominator positive, which is often cleaner for calculations. So the equation becomes, image, formula for CB equals, MWCW, T, TW, divided by, MB, TB, T, C block equals, M water C water, T, TW, divided by, M block, TB, T. Now, let's plug in our numerical values. We know, M water equals 1.1 kilograms, D water equals 4186 J divided by, kgK. This is a standard value you'll find in our textbook. The specific heat of water, T, equals 21.4 degrees Celsius, TW equals 20.0 degrees Celsius, M block equals 0.50 kilograms, TB equals 54.5 degrees Celsius. Let's calculate the temperature differences. TW equals 21.4 degrees Celsius, 20.0 degrees Celsius, equals 1.4 degrees Celsius, or 1.4 K. Since it's a change in temperature, T equals 54.5 degrees Celsius, 21.4 degrees Celsius, equals 33.1 degrees Celsius, or 33.1 K. Now, substitute these into our equation for C block, image, full substitution step on the slide. CB equals 1.1 kilograms, 4186 J divided by, kgK, 21.4 degrees Celsius, 20.0 degrees Celsius, divided by, 0.50 kilograms, 54.5 degrees Celsius, 21.4 degrees Celsius, C block equals, 1.1 kilograms, 4186 J divided by, kgK, 1.4 K, divided by, 0.50 kilograms, 33.1 K. Let's do the arithmetic. Numerator, 1.14186 1.4 equals 6446.44 J. Denominator, 0.5033.1 equals 16.55 kgK. So, C block equals 6446.44 J divided by 16.55 kilograms K. Image, final result, equals 390 J divided by, kgK, and when you perform that division, you get approximately 389.51 J divided by, kgK, which we round to 390 J divided by, kgK. So, the specific heat of this metal block is 390 joules per kilogram Kelvin. What does this tell us? If you look back at tables of specific heats, you'd find that copper has a specific heat very close to this value, around 387 J divided by, kgK. So, our mystery metal is likely copper. It's also interesting to observe the final temperature. It's 21.4 degrees Celsius, which is much closer to the water's initial temperature, 20.0 degrees Celsius, than to the metal's initial temperature, 54.5 degrees Celsius. Why is this? There are two main reasons here, as our textbook insight highlights. First, the mass of the water, 1.1 kilograms, is more than double the mass of the metal block, 0.50 kilograms. More mass means more stuff to heat up or cool down. Second, and even more importantly, water has an exceptionally high specific heat, 4186 joules per kilogram K, compared to our metal, 390 joules per kilogram K. This means water requires a lot more energy to change its temperature by 1 degree than most other substances, including our metal. So, it effectively dominates the final temperature, resisting change much more strongly than the metal. This is why it takes so much energy to boil water, and why oceans moderate global temperatures. This example beautifully illustrates the power of the conservation of energy and the concept of specific heat in understanding how different materials interact thermally. Turning our attention to latent heats. Now, this is where things get really fascinating, and perhaps a little surprising at first glance. The slide poses a great question right away. When two phases coexist, something surprising happens. The temperature remains the same even when you add a small amount of heat. How can that be? You're adding energy, but the thermometer isn't budging. It's like you're putting money into an account, but the balance isn't increasing. To really get to the bottom of this, let's cast our minds back to our apartment building analogy. Remember how we were building that high-rise? You, the owner, were giving me, the contractor, money, and in return, the building would add more floors. But then, at a certain point, you kept giving me money, but the building stopped growing taller. You'd come to the site, scratching your head, asking, Dr. Mohammed, where is all that money going? The building isn't getting any higher. Well, the answer then, and the answer here, is that the energy wasn't wasted, it was just doing hidden work. It was like I was taking your money and doing all the internal finishing, the plumbing, the electrical, the painting, within those existing floors. It didn't add to the visible height, but it was crucial work happening inside. It's exactly the same idea with this ice cube example on the slide. Let's imagine we have an ice cube, initially chilling at a frosty -10 degrees Celsius. If we start adding heat, Q, what happens? Its temperature dutifully rises, following our familiar Q equals mcΔT relation. It goes from -10 degrees Celsius to -5 degrees Celsius, then maybe to -2 degrees Celsius, and so on. The thermometer is climbing, just like our building was adding floors. But then, the ice cube's temperature reaches 0 degrees Celsius. Now, here's the magic, the surprise, that the slide highlights: even if you continue to add more heat, the temperature of that ice-water mixture does not increase. It stays stubbornly at 0 degrees Celsius. So, where is this heat going? Is it just vanishing? Absolutely not. Just like our building analogy, this added heat is going into crucial internal work. Instead of increasing the overall kinetic energy of the molecules, which is what temperature measures, this heat is being used to convert some of the ice into water. On a microscopic level, that added heat energy is making the water molecules in the solid ice vibrate with enough energy to actually break loose from their tightly bound positions in the crystal lattice. They gain enough energy to overcome those intermolecular forces and become part of the more fluid, less structured liquid phase. So, the heat isn't raising the temperature, it's changing the phase of the substance. It's literally transforming the ice's internal structure from a solid to a liquid. This hidden energy, this energy that doesn't manifest as a temperature change but instead goes into a phase transition, is precisely what we call latent heat. It's latent because it's there, it's very real, but it's hidden from our thermometers during the phase change. Pretty neat, isn't it? Moving on to our next fascinating concept, we're going to talk about latent heats. Now, this is where physics gets a little mysterious, almost magical. Remember our apartment building analogy? We said that as you add money, the building goes up, right? More floors, more height, that was like adding heat and seeing the temperature rise. Well, with latent heat, it's a bit different. Imagine you're still putting money into the building, but for a while, it doesn't get any taller. You're thinking, where's my money going? But actually, the money isn't being wasted, it's just being used for something inside the building. Maybe you're installing the plumbing, doing the wiring, or adding beautiful finishes. The structure of the building is changing, but its outward height isn't. That's precisely what latent heat is. As the slide defines it for us, the latent heat, L, is the heat that must be added to or removed from 1 kilogram of a substance to convert it from one phase to another, without change in temperature. Did you catch that crucial phrase? Without change in temperature. This is the hallmark of latent heat. All the energy you're putting in isn't raising the temperature, it's doing the internal work of changing the substance's phase, like turning ice into water, or water into steam. We define latent heat, L, using the formula, L equals Q divided by M. Here, Q is the total amount of heat energy involved, and M is the mass of the substance undergoing the phase change. From this definition, the unit of latent heat, as you can see, is joules per kilogram, joules per kilogram. It's the energy per unit mass needed for this transformation. Naturally, if we want to find out the total amount of heat Q required for a given mass M to change phase, we can rearrange the formula to Q equals mL. This tells us exactly how much energy is hidden or latent within that phase change. Now, just like there are different phases, there are different types of latent heat. First, we have the latent heat of fusion, LF. This is the heat required to melt a solid into a liquid, or conversely, to freeze a liquid into a solid. Think about ice melting in your drink. It absorbs a significant amount of heat to change from solid ice to liquid water, all while staying at 0 degrees Celsius. That's the latent heat of fusion at work. Next, we have the latent heat of vaporization, LV. This is the energy needed to convert a liquid to a gas, like boiling water into steam, or condensing steam back into water. This is a huge amount of energy. For water, as indicated on the slide, the latent heat of vaporization, LV, is 2.26 times 10 to the power of 6 joules per kilogram. That's a massive amount of energy just to turn a kilogram of water into steam, without even raising its temperature past 100 degrees Celsius. This is why a burn from steam is often far more severe than a burn from boiling water. The steam carries all that extra latent energy. Finally, though less co-millimeter sun in everyday experience, we have the latent heat of sublimation, LS. This is the heat required to convert a solid directly to a gas, bypassing the liquid phase altogether. Think of dry ice, solid carbon dioxide. It doesn't melt into a puddle, it sublimes directly into a gaseous state, absorbing latent heat in the process. So, in essence, latent heats are about the energy investment in changing the fundamental arrangement of molecules, not just speeding them up to increase temperature. It's the building doing its internal renovation before it adds another floor. It's a critical concept in understanding how substances interact with heat, especially during phase transitions. Now, consider this. This graph, image tag for graph, is a fantastic visual representation of what happens when we add or remove heat from a substance, specifically water, and how its temperature responds. It's titled Temperature versus Heat Added or Removed, and it really tells a story of transformation. Let's start with the scenario given here. Image tag for bullet point. Initially 1 kilogram of H2O is in the form of ice at -20 degrees Celsius. So, we begin our journey down here, at a chilly -20 degrees Celsius, with our kilogram of ice. As we start adding heat, moving along the x-axis to the right, what happens? The temperature of the ice begins to rise. You can see this as the first upward sloping line on the graph, image tag for first sloped line, from -20 to 0 degrees Celsius. The ice is absorbing energy, its molecules are vibrating faster, and its temperature increases steadily. This is what we expect, right? More heat, higher temperature. But then, something fascinating happens when we reach 0 degrees Celsius, image tag for flat line at 0 degrees Celsius. Even though we continue to pour in heat, the temperature stops rising. It stays stubbornly at 0 degrees Celsius for a significant amount of added heat. Why is that? Remember our apartment building analogy? When you were building the first few floors, the height of the building was increasing. That's like the temperature increasing. But then, for a while, even though you kept pouring money into the project, the building didn't seem to get any taller. Instead, you were spending that money on the internal finishing, the plumbing, the electrical work, the paint. The building was transforming internally, even if its visible height, temperature, wasn't changing. That's precisely what's happening here. The added heat isn't increasing the kinetic energy of the water molecules, which would show as a temperature rise. Instead, it's being used to break the bonds holding the water molecules in their rigid, crystalline ice structure. It's literally transforming the ice at 0 degrees Celsius into liquid water at 0 degrees Celsius. This hidden energy, the energy spent on changing the phase, is what we call latent heat of fusion, denoted here as QF equals MLF. All that energy goes into melting the ice, not warming it. It's quite clever, isn't it? Nature knows how to prioritize. Once all the ice, our 1 kilogram, has completely melted into water at 0 degrees Celsius, that's the end of our first flat line, at point B on the graph. Then if we continue to add heat, the temperature starts to climb again, image tag for second sloped line, from 0 to 100 degrees Celsius. Now we have liquid water, and as it absorbs heat, its temperature increases, just as you'd expect. It rises from 0 degrees Celsius all the way up to 100 degrees Celsius. And then, history repeats itself. At 100 degrees Celsius, image tag for flat line at 100 degrees Celsius, we hit another plateau. Again, we're adding heat, but the temperature is not changing. It remains fixed at 100 degrees Celsius. This is the boiling point, and once again, our building isn't getting taller. The energy is being used for another internal renovation. This time, the heat is breaking the remaining intermolecular bonds in the liquid water, allowing the molecules to escape into the gaseous state, steam. This is the latent heat of vaporization, labeled QV equals MLV. The water at 100 degrees Celsius is transforming into steam at 100 degrees Celsius. It's a massive energy investment to make that change from liquid to gas. Finally, once all the water has converted into steam at 100 degrees Celsius, at point D on the graph, any further heat added will once again cause the temperature to rise, image tag for third sloped line, above 100 degrees Celsius. Now we're heating steam, and its temperature will continue to increase. You can also see the arrows pointing left, representing the reverse processes, condensation, steam back to water at 100 degrees Celsius, and freezing, water back to ice at 0 degrees Celsius. In these cases, heat is removed from the system at a constant temperature. So, this graph beautifully illustrates how heat isn't always about making things hotter. Sometimes, it's about changing the fundamental arrangement of matter itself, transforming it from one phase to another, at a constant temperature. These phase changes, governed by latent heats, are absolutely crucial phenomena in thermal physics. What a journey for our humble kilogram of water, from ice to boiling steam. Turning our attention now to conceptual checkpoint 4 to 3, severity of a burn. This is a fantastic question that really makes us think about the hidden energy we just discussed. The question states, both water at 100 degrees Celsius and steam at 100 degrees Celsius can cause serious burns. Is a burn produced by steam likely to be, A, more severe than, B, less severe than, or, C, the same as a burn produced by water? To answer this, let's cast our minds back to our analogy of the apartment building. Remember when you, the owner, gave me, the contractor, money, but the building's height, temperature, didn't increase? Why was that? Because that money, that energy, wasn't being used to raise the overall height. Instead, it was being invested internally, perhaps finishing the plumbing, adding plaster to the walls, or laying tiles. This was the latent heat, the energy that was hidden, causing a phase change rather than a temperature change. Now, apply this idea to water and steam at the same temperature, 100 degrees Celsius. Imagine we start with water at, say, 50 degrees Celsius. As we add heat, its temperature rises. This is like the building growing taller. We use the formula Q equals mcΔT, refer to figure 4.9 in textbook, specifically the sloping segments. Eventually, the water reaches 100 degrees Celsius. At this point, something interesting happens. If we continue to add heat, the temperature doesn't immediately go above 100 degrees Celsius. Instead, that added heat is used to transform the water from its liquid state into steam, without a change in temperature. This is our latent heat of vaporization. Refer to figure 4.9 in textbook, specifically the horizontal segment for vaporization. It's like all that money going into the internal finishing of our building without adding another floor. So, here's the crucial difference. Water at 100 degrees Celsius has received enough energy to reach that temperature. Steam at 100 degrees Celsius, however, has received all that same energy, plus the additional, substantial amount of latent heat required to change its phase from liquid water to gas, steam. This latent heat of vaporization for water is about 2.26 times 10 to the power of 6 joules per kilogram. LF for water is 3.35 times 10 to the power of 5 joules per kilogram, LV for water is 2.26 times 10 to the power of 6 joules per kilogram, refer to table 4.3 in textbook. That's a huge amount of extra energy packed into that steam, making its heat content much higher than that of water at the same temperature. When steam comes into contact with your skin, it doesn't just cool down. First, it has to condense back into water at 100 degrees Celsius, and in doing so, it releases that massive amount of latent heat of vaporization directly onto your skin. Then, that 100 degrees Celsius water proceeds to cool down, releasing even more heat. Water at 100 degrees Celsius, on the other hand, only releases the heat as it cools down from 100 degrees Celsius. Therefore, the total amount of energy transferred to your skin from steam at 100 degrees Celsius is significantly greater than from water at 100 degrees Celsius. This additional energy transfer is what causes the much deeper and more severe burn. So, the answer to our checkpoint question is clearly, A burn produced by steam is likely to be more severe than a burn produced by water. It's all about that hidden energy. Let's explore a very cool, and delicious, application of latent heat, how we make homemade ice cream. This isn't just a kitchen trick, it's pure thermal physics in action. Imagine you're making your own ice cream. You've got your lovely, sweet mixture in a container, and you typically place this container into a larger bucket filled with ice and water. This is your cooling bath. Now, here's the ingenious step. You add salt to that surrounding ice-water mixture, not directly into your wonderful ice cream, of course, that would be a salty surprise. What happens when you add salt? The dissolved salt molecules, or ions, become like little busybodies in a crowded room. They get right in the way of the water molecules. For water to freeze and form solid ice, its molecules need to align themselves in a very specific, ordered crystal structure. They need to interact with one another and freeze, essentially shaking hands and forming strong bonds. But when salt ions are present, they block these interactions, making it much harder for the water molecules to achieve that necessary ordered arrangement for freezing. Because these salt molecules interfere, the system of ice and water can no longer be in equilibrium at the usual 0 degrees Celsius. It's like, remember our analogy of Ahmed and Hussein in a room? If they usually reach a stable state at a certain temperature, but now a third party, the salt, is actively disrupting their interactions, that stable temperature is no longer achievable. A lower temperature is now required for the water to solidify into ice. It needs to get even colder to overcome the disruptive presence of the salt. So, what's the consequence? The ice in your surrounding mixture, which now finds itself at 0 degrees Celsius but unable to maintain equilibrium with the salty water, begins to melt. It's trying to reach that new, lower freezing point. And to melt, what does ice need? Latent heat. Remember our apartment building analogy for latent heat? This energy isn't raising the temperature of the ice, it's going into breaking the bonds to change its phase from solid to liquid. And where does this heat come from? It's a thermal sponge, eagerly absorbing heat from its surroundings. And what's right next to it? Your ice cream container. By continuously drawing this required latent heat from your ice cream mixture, the ice cream gets significantly colder, much colder than plain ice and water could ever make it. This combined action of salt and melting ice creates an environment that can drop to several degrees below 0 degrees Celsius, which is absolutely perfect for freezing your homemade treat quickly and effectively. That's the magic of latent heat and a little bit of salt. Let's explore this fantastic example, steam heat, which truly brings together everything we've learned about specific heat and latent heat. Imagine you're in the lab, a true physicist, and you're given a task: make some steam. The problem states you're adding a total of 5.60 times 10 to the power of 5 joules of heat to 0.220 kilograms of water, starting at an initial temperature of 50.0 degrees Celsius. Our ultimate goal is to find the final temperature of the steam after all that heat has been absorbed. Now, this isn't a simple one-step process, my friends. Look at our beautiful graph here. Point to graph, starting at initial, at 50 degrees Celsius, it tells the whole story, a journey of energy and transformation. You see the temperature on the vertical axis and the heat added on the horizontal axis. First, your water is at 50 degrees Celsius. Point to initial, on graph, then to 50 degrees Celsius mark on the temperature axis. Before it can even think about becoming steam, it needs to reach its boiling point. So, the first stage, which we call Q1, point to Q1 section on the heat added axis, and the corresponding sloping line segment labeled water, is all about heating that liquid water from 50 degrees Celsius up to 100 degrees Celsius. During this stage, the temperature is steadily increasing, which means we're dealing with the specific heat of water. Let's calculate Q1. Point to Q1 calculation in the formula section. We use our familiar formula, Q1 equals mass, m, times the specific heat of water, seawater, times the change in temperature, delta T. Our mass is 0.220 kilograms. The specific heat of water, that magnificent constant, is 4,186 joules per kilogram per Celsius degree. And our delta T for this specific stage is the final temperature, 100 degrees Celsius, minus the initial temperature, 50 degrees Celsius, giving us a change of 50.0 Celsius degrees. Plugging those numbers into the equation, we get Q1 equals 0.220 kilograms, multiplied by 4,186 J divided by kg C degrees, multiplied by 50.0 C degrees. This calculation yields 4.60 times 10 to the power of 4 joules. So, that's the energy we've spent just getting our water hot enough to boil. But wait. Once it hits 100 degrees Celsius, it doesn't just instantly turn into steam, does it? No. Point to the vaporization, flat line on graph. This is where the magic of a phase change happens, and with it, our second stage, Q2. Point to Q2 section on the heat added axis. Notice how the graph becomes flat. The temperature stays stubbornly at 100 degrees Celsius, even though we're still pouring energy into it. Remember our apartment building analogy? When the temperature isn't increasing, it's like we're not adding new floors to the building. Instead, we're spending the money, the energy, on something else, internal renovations. In the case of water turning into steam, this hidden energy, this latent heat, is used to overcome the intermolecular forces between water molecules, allowing them to escape as a gas. It's not visible as a temperature rise, but it's absolutely crucial for the physical transformation. So, for Q2, we use the latent heat of vaporization formula, Q2 equals mass, m, times LV, the latent heat of vaporization. Point to Q2 calculation in the formula section, our mass is still 0.220 kilograms. And the latent heat of vaporization for water, LV, is a substantial 2.26 times 10 to the power of 6 joules per kilogram. That's a lot of hidden energy. Multiplying those values, Q2 equals 0.220 kilograms, multiplied by 2.26 by 10 to the power of 6 joules per kilogram. This gives us a whopping 4.97 times 10 to the power of 5 joules. Look at that. Much more energy is needed for the phase change than just heating the water to boiling. This is why steam burns are so much more severe than hot water burns. As we discussed previously, steam holds a tremendous amount of latent energy. Now, let's take a moment to tally up our energy consumption so far, Q1 plus Q2. Q1 was 4.60 by 10 to the power of 4 J, Q2 was 4.97 by 10 to the power of 5 J, adding them. 4.60 by 10 to the power of 4J plus 4.97 by 10 to the power of 5J equals 5.43 times 10 to the power of 5J. Our problem stated we added a total of 5.60 by 10 to the power of 5J, refer back to the problem statement for total heat, since 5.60 by 10 to the power of 5J is greater than 5.43 by 10 to the power of 5J. It means we have more energy than what was needed to heat the water to 100 degrees Celsius and completely convert it into steam at 100 degrees Celsius. Excellent. This tells us our steam is going to get even hotter, entering the third phase of the process. Point to the third sloping line segment labeled steam. So, how much energy is left to heat this superhot steam? This is our Q3. Point to Q3 calculation in the formula section. Q3 equals the total heat added minus Q1 minus Q2. That's 5.60 by 10 to the power of 5J minus 4.60 by 10 to the power of 4J minus 4.97 by 10 to the power of 5J. A quick calculation reveals that Q3 equals 17,000 joules. This is the amount of energy that will go into increasing the steam's temperature above 100 degrees Celsius. Finally, for the third stage, where we're heating the steam, we'll use our specific heat formula again, but this time specifically for steam. We know Q3 equals mass, m, times the specific heat of steam, C steam, times the change in temperature, delta T. Point to delta T calculation for steam. We want to find delta T, so we rearrange the equation, delta T equals Q3 divided by, mass times specific heat of steam. Q3 is 17,000 joules, which we just calculated. The mass is still 0.220 kilograms, since all the water has now become steam. And the specific heat of steam, it's different from liquid water, remember? Is 2010 joules per kilogram per Celsius degree. So, delta T equals 17,000 J divided by, 0.220 kilograms multiplied by 2010 J divided by, kg C degrees. This gives us a temperature increase of 38 Celsius degrees for the steam. Now, remember, the steam started at 100 degrees Celsius after the phase change was complete. Point to 100 degrees Celsius on the graph. At the end of the vaporization plateau, we just calculated that it increased its temperature by another 38 degrees. So, the final temperature of our steam is 100 degrees Celsius plus 38 degrees Celsius, which gives us a final temperature of 138 degrees Celsius. Point to the final and 138 degrees Celsius result on the slide, voila. The system is completely converted to steam, and it's heated well beyond its boiling point. This example beautifully illustrates the different energy requirements for raising temperature and for changing phase. It's like paying for the basic structure of the building, then doing all the internal work, and then adding more height if you have any leftover budget. Keep up the excellent work, future physicists. Moving on to our next topic, and a very important one in thermal physics, we have, image, slide 16 showing, thermal expansion, title, thermal expansion. Now, my dear students, this is a concept you observe all around you, perhaps without even realizing the physics behind it. What is it? Simply put, most substances expand when heated. And conversely, they contract when cooled. Think about it, why would this happen? Remember our apartment building analogy? We talked about the workers, the molecules, receiving money, that is, energy or heat, and becoming more energetic, increasing their activity, right? Well, it's a similar idea here. When you give these molecules more energy, they vibrate more vigorously, they start moving around with greater amplitude. And what happens when many people in a crowded space start moving more energetically? They need more space, they push against each other, don't they? That's precisely what happens on a microscopic level. The increased vibration of the atoms or molecules causes them to push further apart from their neighbors, and this collective pushing results in an overall increase in the size of the material. The slide gives us a perfect example. Power lines on a hot mm day hang low compared to their appearance on a cold day in winter. You see these big, long wires, usually made of metal, right? In the scorching mm heat, they absorb a lot of thermal energy, their molecules get very excited, they expand, and the wires lengthen, causing them to sag. But come winter, when the temperature drops, the molecules calm down, they contract, and the wires pull taut again. It's a direct consequence of this thermal expansion. Another everyday application, also mentioned on the slide, is how thermal expansion is the basis for many thermometers, including the familiar thermometers used for measuring a fever. How does that work? Inside that small glass tube, you have a liquid, perhaps mercury or colored alcohol. When it gets hotter, this liquid expands. Because the tube is very narrow, even a tiny expansion in volume translates into a noticeable rise in the liquid's column. This height then corresponds to a temperature reading. Elegant, isn't it? A simple physical principle giving us a precise measurement. Now, while this expansion upon heating is the co-millimeter-sun response for most substances, physics always has its surprises, doesn't it? The slide highlights a bizarre substance that is an important exception to this rule: water. Yes, the very substance you drink every day has some very special and unusual thermal behavior, especially in a specific temperature range. Most materials contract when cooled. Water does this too, but only down to a certain point. Then, something peculiar happens, it starts to expand as it gets colder before it even freezes. This unusual thermal behavior of water has profound consequences for life on Earth, something we'll explore in more detail very soon. It's one of those unique properties that make water, well, water. In this section, thermal expansion, we'll look at it in different dimensions. We'll talk about linear expansion, which is a change in length, area expansion, which is a change in surface area, and volume expansion, which is a change in the overall three-dimensional size. For now, we are starting with linear expansion, which is often the easiest to visualize and understand. We'll delve into the equations and more specific examples for each of these in our upcoming discussions. So, prepare yourselves for some fascinating insights into how materials respond to temperature changes.